because when you're replicating DNA, you need to have, it has to be able to come apart, right? So it can make a copy of itself. Or when it's making proteins, it has to come apart so that the code can be paired up with messenger RNA, which carries the amino acids, and then goes to assembles the proteins. So super important that it can do that. All right, we are on the last page. We talked about the two big ones. I don't even have notes for dipole on your notes, because basically hydrogen bonding is a dipole-dipole interaction. It's just a specific one that just works with fluorine, oxygen, and nitrogen. So dipole-dipole interactions are just any dipole with another. So for instance, like hydrogen chloride there. It's got a dipole, right? I think I have a picture of it here, yeah. So I don't have any notes for this. Basically, you just have two, partially positive, partially negative materials that are attracted to others like this. Okay, so it's really the same thing as a hydrogen bond, but that's specific for just three elements. It's just because they're so important, I guess, they get their own name. Okay, and then the next one is a dipole-dipole induced bond or interaction. And this one takes a little bit of explanation. So this is at the top of page 8. So it's a weak interaction that is from a polar molecule or ion inducing a dipole in an atom or non-polar molecule by moving the electrons closer. Not a great definition. I think I can explain it to you guys. Can you look here? And I want to show you. Stick with me here because we're almost done. But I want to show you what an induced charge is, because I think my little yellow and blue blobs are useful to explain this. So on the left you have a blue blob, and it's got a uniform charge distribution. So it's got positives and negatives pretty much equally found. On the right-hand side, they're not uniformly distributed. The two ends have more positives. So they get that little partial positive charge. So what happens is, when the partially charged ends come closer to the uniformly charged blob, what happens is, as you would expect, is because opposites attract, the electrons can move, and they get pulled closer to the right side. So what happens is, you induce, the term is you induce, a dipole in the blue blob, which used to be kind of neutral and have no charge. That's because the electrons kind of got attracted to the right-hand blob. So that's what happens. So what's crazy about this is that you can have a totally neutral molecule, but it can actually momentarily get connected to something else. That's what we call an induced dipole. All right, and the last one is dispersion or van der Waals forces. And these are interesting because we can see them in a couple real life places. They are the attractive force. So this is page 8, number 6. Van der Waals interactions are short-range attractive forces between uncharged molecules from dipole moments. And that you get this dipole moment. So this is where it's crazy. It's not like this permanent dipole, it becomes induced, like we were just talking about. And there's like a moment when it's got a charge on one end and the other end. And so this is where we talked about geckos. I don't know if you remember this, but geckos, they can hang on a glass surface by even using one toe. You can create a great amount of force because each of the little spatula, which are the little projections off their feet, which are on the foot pad, they cover the hair-like setae. Each of those little spatula can have this van der Waals force interaction between the wall or the ceiling and the foot. And remember how they can change, they can lift their foot up. They're not like totally stuck there. They're able to remove their foot. And so it's this making and breaking of these van der Waals forces that allows them to be attracted and then they pull away.